You know, Mary, from here on in, we're going to get pretty heavily into systems engineering.
Yes.
That's way out of your field, isn't it?
You'd be trying to get rid of me by any chance, would you?
No.
Stan, I know I'm not an engineer, but I have been working on this project for 4 years. I'm quite capable of learning more about your systems.
Yes, I know you're quite capable, Mary, and I'd be glad to explain it to you, but there isn't the time. Look, time is money, Mary, especially in space.
It wasn't my idea to produce the vaccine on a space satellite.
No, it wasn't your idea. It was Wilhelm Schroeder's. We're all very grateful to him. I know, Mary, you discovered K-40. But you seem to have forgotten that 4 years ago you'd reached a dead end. There was no way it could be produced commercially. You were in hot water.
So, what you're trying to say is that you can't synthesize K-40?
Well, we cannot do it economically, not as a commercial product. It would be too costly. We have no difficulty in synthesizing the chains of 16 and 24 amino acids, respectively. It is when we come to join the two chains that a problem arises.
To be specific, we have to bond this amino group with this carboxylic group. But when we protect the unwanted groups by chemicals to obtain the correct bonding, the chains are no longer soluble in water or any other solvent.
But I understood that you were using an enzyme as a bonding agent in the final stage to avoid the use of chemicals.
Oh, yes, I used an enzyme to obtain small quantities of K40 for testing. Unfortunately, when the enzyme is separated after the reaction, it is no longer active.
What method are you using for separation?
Well, let me show you. So, in these tubes, we tried different means of chromatography to separate the enzyme from the product and the waste products.
None of them worked?
No. I then tried fixing the enzyme on a resin so it would be recovered by filtration. But still it remained inactive.
The enzyme is very costly. It must be used over and over again if we are to produce K40 in large quantities at a reasonable price.
Yes, I realize that, of course. Surely there must be some way to recover the enzyme so that it still remains active.
We tried chromatographic procedures and countercurrent distribution. In this particular case, they failed. I'm very sorry, Professor.
We are as disappointed as you are, Mary.
Fortunately for you, Wilhelm Schroeder read about your problem. He contacted VPI, and they had the sense to be interested in his proposals.
Mary, I'd like you to meet Wilhelm Schroeder, head of the Space Research and Development Department set up by Meissen and EEAU, Professor Mary Edwards.
How do you do?
Professor Edwards, I'm honored.
And this is Dr. Markowski from the European Space Agency.
Nice to meet you, Professor. My first name is Stanislav, but please call me Stan.
How do you do?
Stan is American, as you may have gathered.
Wow. My folks came from Poland, but I was brought up in the States, so I guess I'm more American than anything else.
What brought you to Europe, Stan?
The European Space Agency made it worth my while.
Well, why don't we sit down?
Thank you.
Coffee, gentlemen?
So, what's it all about, Pierre?
I explained to you on the phone.
Yes, I know, but I still can't believe it. Are you really suggesting that we synthesize K40 in space?
Only the last bonding. In zero gravity, the enzyme can be separated from the product by continuous flow electrophoresis quickly and efficiently.
But isn't there a rotational system of electrophoresis which is very fast?
Oh, yes. We have looked into it, but it's not accurate enough for that particular enzyme.
What exactly is your objection to the space operation?
I'm not objecting. I'm simply surprised. I mean, you say that you can't manufacture K40 on Earth because it's too expensive, and yet now you're suggesting that...
We shan't pay any more than we would have done for a conventional operation on Earth. And we'll only pay at all if the product is satisfactory.
Well, who finances the operation?
Oh, we do, Professor Edwards. My company, EAU, has joined with Nielson in order to develop production units for use in space. And if VPI come in with us, then we'll appoint Dr. Markowski as project director.
This is our opportunity. We can prove to the world that we have the expertise to build production units in space. Space factories.
I see. And if you succeed in manufacturing this vaccine in space, it will attract worldwide interest.
We have that in mind, naturally.
The expense of it all. I mean, how much does it cost to launch a space satellite?
We do not have to launch a satellite.
Maybe I could update the professor on space technology. As you know, all early satellites were put into orbit by rockets.
The United States is ready to try and place its first Earth satellite into orbit.
Even the men who landed on the moon were launched by rocket. And they had to come back the hard way. In fact, rockets, well, like the French rocket Ariane, are still a very effective and economical way of putting unmanned satellites into space. But there's an obvious limitation to a rocket. You can put something into space, but you can't bring it back again. That's why the American space shuttle began a whole new ballgame. For the first time, it was possible to retrieve satellites and bring them back to Earth. It also opened up new opportunities for scientific research. Space Lab, which was constructed in Germany, was fitted in the cargo bay of the Challenger shuttle, converting it into a manned space laboratory. This made it possible to experiment in space and bring the results back to Earth. But still, the experiments were limited by the duration of a shuttle mission. The free-flying version of Space Lab overcomes this problem because it remains in orbit. But experiments in Space Lab are still expensive because of the cost of maintaining manned spacecraft. These new unmanned satellites were developed to provide cheaper facilities. They are placed in orbit by the shuttle and are retrieved with their payloads after experiments are completed.
Well, that's all very well, but surely you still have to put a satellite into space and then bring it back down again.
Not anymore.
ESA is planning to launch a new carrier satellite known as Carsat. It's bigger than the earlier ones, and it won't come back to Earth. It'll stay in orbit indefinitely.
Only the payloads will be brought back to Earth.
Exactly. A shuttle will take up fresh payloads and bring back others in a regular cycle.
So, you see, we have an economical method of putting a production unit into space.
When will this new satellite be launched?
In about 4 years' time. As it happens, it will take us that long to develop the production unit.
It will also take us that long to complete our trials and obtain authorization for the vaccine from the medical authorities.
And are you certain that the electrophoresis process will work in space?
It's been demonstrated several times in Space Lab, for instance, and I have examined the conventional apparatus myself.
Well, I think it all sounds very risky to me.
But we'll be taking the financial risk.
And the risk that you might not get the publicity you expect if the scheme doesn't work.
Professor Edwards, we are as anxious as you are that people should have the vaccine.
Mary, please remember that as things stand, we can't produce K40. I think we should be very grateful for the suggestion.
Very well. Anyway, it's up to you to decide how to produce K40. I have no say in that.
On the contrary, we need your expert knowledge of the biochemical process to help us design the production unit.
I hope you will decide to help us, Professor Edwards. Personally, I'd consider it a privilege to be involved in the production of a vaccine which will save millions of lives. You know what happened after that. VPI agreed to the space project, and you agreed to cooperate. So I came to live in Frankfurt and set up this project office. And from then on, it was planning, planning, and still more planning. The design and development of the production unit became Wilhelm's responsibility. I could see he was imagining his own production unit taking shape when we visited the workshops in England where they build satellites and space packages.
Carsat will be built here. Then it'll be loaded onto the shuttle in separate sections along with the first payloads.
And the astronauts will reassemble it in space.
And after that, the European Space Operations Centre will place it in orbit at a height of 500 kilometres and an angle of 28.5 degrees with the equator. From then on, ESOC will maintain it in orbit. Carsat will use a cold gas system, but we still call it a burn. The gas is released into space and corrects the attitude by its inertial effect. This is where we manufacture the radio antennae. Each payload will have an interface with the platform, including a data link. The antenna on the satellite will transmit the data to one of 3 communications satellites in the geostationary orbit. From there, the signal will be passed back to Earth.
And the energy supplies solar arrays.
Yes. To test the arrays on Earth, we have to stretch them out on a water table to simulate weightlessness. They'll give us an output of approximately 20 kilowatts. Some of that energy will be needed to operate the services on the satellite and refill the storage batteries which are used when the satellite is in the Earth's shadow. The rest is available for the payloads.
What's the voltage?
28 DC. The user can convert that inside his payload to whatever he needs.
Mr. Jackson, do you think you'll get it ready on time?
We must. It's too late to cancel our reservation on the shuttle.
Carsat was completed on time, and the shuttle was launched 2 weeks ago. Our own production unit was one of the first payloads. The astronauts assembled the sections in space and located the payloads at their berthing ports. Then the controllers at ESOC took over. It was their job to put Carsat into the correct orbit. When that was achieved, the control of the operation was switched to a control room specially for Carsat. Here the operations team set to work. They commissioned the payloads to begin production, one after another, including our own.
Payload 6, K40 vaccine unit. Begin operations. Open buffer valves EP60AA1 and EP60AA2. Start pump motor EP10AP1, speed 10% of maximum.
And everything was going well. We thought we'd solved your problem. Till yesterday.
You're quite right. We had to go into space. I'm sorry, Stan.
That's okay. Right, let's get on with this investigation. You know, we're going to make a great team together, you and I. What with your brains and my beauty.